Get to the third part of this semester. It's about complex analysis. So chapter 13 covers basic definitions and introduce the concept of complex differentiation. All right, and so I will start with the second section. Okay, we know we can represent complex numbers in a complex plane. So this is the imaginary part. This is the real part. And the y is the imaginary part of a complex number. So, so here, xy. Okay, so we use a point in the complex plane to represent a complex number z. Right? So z is equal to x plus iy, and so x is called the real part of z. And the y is called the imaginary part of z. Right. So this is the so-called the Cartesian coordinate representation of a complex number. Okay, coordinate representation. And we know that in the point, any point, basically we have polar representation. Okay? And so we know that with polar representation, we have x is equal to r cosine theta, y is equal to r sine theta. All right. So we change the Cartesian coordinate into the polar coordinate, and so the Cartesian coordinates can be represented by the polar coordinate, okay, with such a coordinate transformation. And also we know that r is equal to the square root of the sum of square of the real part and the imaginary part of the complex number. Okay. All right. And we know that we can also write in this way. So we know zr is the so-called complex conjugate of the y. So this is called a complex conjugate. Of z. Okay, so z bar is defined to be x minus iy. Okay, and the theta, and also theta is denoted as a function of z. So we say the argument. So this is the argument. Okay, so and we just denote theta as argument of z, and so we know that tangent of theta actually is y divided by x. Okay, this is the theta. Okay, so from this you know. So theta, when the angle, so the theta actually has multiple multi-valued. So it is which is multi-valued okay, function. Alright, so to define. So for function, it is possible to be multi-valued, so for real function. But in here, we abused the usage of a function to say that this is a multi-valued function. Okay? So corresponding to one z, okay? So z here, so z is represented by a point xy. And for the same z, the theta can be this angle plus 2 pi plus 2 pi times a, alright? Okay? So, so basically, when theta is added by an integral multiple of 2 pi, then you will get the same x and y. So that means that you get the same complex number. So that's why theta can be multi-valued. Okay? And so in complex analysis, we'll say the principal, all right, the principal value. So we will define the principal value, denoted as A, R, G, Z of little a, R, G, Z of this multi-valued function is defined by the restriction, the ARG Z will be less than or equal to pi by greater than minus pi. Okay? So thus ARGZ is a real an actual function of z, because each z corresponding to a value, an angle. Okay? And we have, so we can say the multi-valued function little argz. Argz is the principal value plus 2 pi to m pi. Okay, for all n in the set of all integers. Okay, so that's why that this is multi-value. So this is the description. Okay. Okay, a simple fact is that. All right. So now. All right. So note that z, okay, can be written as r cosine theta plus I sine theta. So this can be written as r cosine theta plus I sine theta. Okay. Right. So the same z, the same complex number can be represented in the coordinate, Cartesian coordinate, or can be used the polar coordinate r and theta here. And of course, the theta, we should say that theta is multi-valued. Okay, remember we have this one. Theta is the little arg. See. Okay. Right. Okay. So now the fact. If z1 is equal to 1 cosine theta 1, plus I sine theta 1. And the Z2 is another complex number, cosine theta 2 plus I sine theta 2. Alright, so if we have that, then the product, okay? So we can do the product. The product, of course, you can use the Cartesian coordinate representation to compute the product, okay? But when represented by the polar system, we will see that this is become to theta 1 plus theta 2 I sine theta 1 plus theta 2. Okay. So we have this identity. So if we represent Z1 to be R1, alright, this is polar representation, and the Z2 can be represented in this way. Then the product, okay, it can be composed to this is the length, okay, the length of Z1 Z2 here. So the length of Z1, this product is R1 times R2, and the argument becomes to the sum of the argument of Z1 and Z2. Alright, that is very convenient to write it down. Okay, so the proof is quite straightforward. So we know this is R1, R2, and so we have cosine theta 1 plus I sine theta 1, cosine theta 2 plus I sine theta 2. Okay, right, and then okay, you can have the real part. So this is the real part, and the imaginary part. We have cosine theta 1 and theta 2 plus, okay, I just write down theta 1. Okay, we have that. And by the sum angle theorem, we have, so this is theta 1 plus the cosine theta 1 plus theta 2. And here, this is the sine theta 1 plus theta 2. Okay. How about the other? If the ratio, then the ratio becomes to R1 divided by R2, and cosine theta 1 minus theta 2, and I minus theta 2. Okay? If Z2 not equal to 0. Okay? Alright. So if Z2 not equal to 0, so if Z2 not equal to 0, then R2 not equal to 0, okay? So not equal to 0 because it's here. And then, so Z1 divided by Z2. Z1 divided by Z2 is R1 divided by R2 times cosine theta 1 I sine theta 1 cosine theta 2 plus I sine theta 2. Okay, we have that. And so we multiply cosine, the complex conjugate of the denominator. This is very common to perform in high school. Okay, so we have cosine theta 2 minus I sine theta 2. Okay, right? And now the denominator becomes to cosine square theta 2 plus sine square theta 2, which is equal to what? Okay, so the denominator is equal to 1. And so we have cosine theta 1. So you multiply and this one, and you have cosine theta 1, cosine theta 2, plus sine theta 1, sine theta 2. Okay? So here is the real part, and the imaginary part is sine theta 1, cosine theta 2, minus cosine theta 1, sine theta 2. Okay? And again, by the difference angle theorem, we have 2. So this is cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So we get the result. Okay? So this is some simple algebra we can have. Okay? So this is the simple way to. So we have two identities. This result give us two identities. One is that the multi-value function. Okay, so the argument of z1 times z2. The argument of z1 times z2 is theta 1 plus theta 2, right? So this is equal to the argument of z1 plus the argument of z2. Okay, immediately we have that. The second thing is that the argument of z1 divided by z2 is equal to the argument of z1 minus the argument of z2. If z2 is not equal to 0. Right? Okay. Now the extension. So now we prove we will prove the Dimois formula. Okay, the Dimois formula is saying that if z is equal to r cosine theta plus I sine theta, then the nth power of z is equal to r's nth power, and the argument is n theta plus I sine n theta for all n equal to z. Okay, for any integer n here. Okay, it's called Dimois formula. Okay, and so the proof, well, you can apply so by induction. Okay, by induction. So it's that. Why? Because okay, for n equal to 1, fine. For n equal to 0, for n equal to 0, z to the zeroth power will always define to be 1. So R0 is 1, and this is 0. Cosine 0 is 1, sine 0 is 0. It's 1. How about n equal to 2? For n equal to 2, you can apply here z1, z2 are equal to z. Okay? So when z1, z2 are equal to z, then theta 1 is equal to theta 2, right? And so z squared has argument which is 2 times theta, because the theta 1 and theta 2 are the same. Okay? So you have 2 theta here. Okay? And by induction, you can prove that. How about when n is negative integer? Well, you apply here. Okay? You apply here. when n is minus 1, right? When n is minus 1, well, when n is minus 1, then z1 is 1, z2 is z, okay? So this is 1 and r2, okay? So it becomes r minus 1, and you can have this theta 1 is 0, theta 2 is theta. So it becomes minus theta. So minus theta when n is minus 1. Okay? So you apply the second formula here. And then you can apply the n when n is positive. Okay? So basically this is by induction. So the one formula is very simple once you know the facts here. Any questions? Do you need me to do the induction? So fine, right? Good. Okay. So now we will deal with truth. Right, so we let n greater than equal to 1 be an integer. Right, so positive integer. Now nth root. Right, and nth root of z. C means the set of all complex numbers, as we know. It's the complex number. We say w such that the nth power of w is equal to z. Right? So we call a complex number w is an nth root of a particular complex number z if this equation is satisfied. If we raise the nth power of w equal to z. So any w satisfying this equation is called an nth root of z. Okay? It's called an nth root of z. Right. Now, if z equals to 0, of course, then there is no other choice. W should be 0. Right? So it's the only root. So you have only the only nth root. Right? So when z is 0, you have only one nth root, which is equal to 0. No others. So now consider z not equal to 0, i.e. r not equal to 0. Okay? Alright. So now we let z, so we represent z to be with polar form and w also is represented by cosine phi plus I phi. Okay? Now the equation implies that, so now we apply De Morgan's formula, right? The De Morgan formula gives us that x to the nth power cosine n phi plus I sine n phi must equal to r cosine theta plus I sine theta. Okay, so we have that. So that means that, so the economic condition is that the r, that x nth power is equal to r, okay, and the phi is equal to m phi is equal to ARZ. So this is equal to Z. Okay, and this is ARZ plus 2m pi. Okay, M Z. Okay, so we have if and only condition. And so that means that S should be the nth root of R. You know, R, S, they are all positive numbers. So this is unique. And we have, say, phi is equal to ARGC divided by N plus 2 pi M divided by N. Okay? Alright, so we define sub K to be R cosine phi K, right? With phi K equal to AR argument Z divided by N plus 2 pi K N, for K from 0 to N minus 1. Okay, 1, 2. Okay, because when K equal to N, you have 2 pi. So when you have 2 pi, you substitute into here, you get the same result. So you will have periodic, alright? So you have periodic solutions. So WK are nth root of Z. Right? So how many nth roots do we have? Well, we have n nth roots. So if Z is non-zero, then to find the nth root of Z, we will find n such roots. Okay, so we have n nth roots of Z. Nth root Z. Okay, remember, the capital ARG is an actual function. So this is a single value function. So you get some definite value here. And here, the plus part, the additional part is 2 pi over n times k. Okay, so k is from 0 to n minus 1. So that is the root we have. Okay. All right. So a convenient way to represent nth root is that we let omega n to be cosine 2 pi n plus I sine 2 pi n. Okay, so let's just think about this one. So what is omega n? Omega n, which are which is an nth root of 1. Okay? So this is z equal to 1. So if the complex number is 1, 1 is real number, okay? It's a real number. But when we want to find the complex nth root, we we find this is one of the nth root of z. All right. So specifically, this unit circle. So this is the theta is equal to 2 pi divided by n. Okay. So this number is omega n, represent omega n. Cosine 2 pi divided by n. Sine 2 pi divided by n. Okay? Yeah? So this point represents omega n. It's a complex number. And this complex number is an nth root of z. Okay? And from here, we know by the Moore formula, the nth root of 1 are 1 omega square up to omega n minus 1. Okay? So it's very easy. With omega n, forgot to put n. 1 omega n square omega n to n minus 1's power. Okay? So we have n complex numbers, right? Which are nth root of 1. Okay. Remember, you know, omega n's power is equal to 1 because omega n is the. So this is to say that omega n is the nth root of 1 because when you raise n's power, it becomes 1 by the Moore formula, right? So if z not equal to 0, right? Then w is an nth root of z. Then w omega n square w omega n to n minus 1 are the nth root of z. Okay? So it's very easy to represent the nth root. So if z is not equal to 0 and you know w is an nth root of z, you find 1. Okay? Then the others can be constructed very easily. Just multiply with the omega n, square of omega n up to multiply with n minus 1's power of omega n, etc. So it's very easy to represent that. Alright? So next, we will talk about complex differentiation. Okay? Geometric okay. To talk about differentiation, we have to know something about geometry, okay, of the complex plane. Okay, so let's say that a neighborhood neighborhood right? A neighborhood of a point A and C, right? It's a subset of C such that okay. So geometry, this is the distance, right? Because we represent a point, okay, in the compass plane by a compass number. So z minus a, and take the absolute value, is just the distance, right? So the distance is less than 0, all right? And so this is actually it is called a neighborhood, okay? It's called a neighborhood. Okay, sometimes people call it as rho neighborhood. All right, to indicate what is the diameter of rho. Okay, but in many situations, the diameter of the neighborhood is not essential. So well, we just know that that is a diameter, or rho greater than 0. That's fine. All right. So so the concept. So one about a neighborhood of a point A in the compass plane. Specifically, is something like this one, and this is called open ball. So basically, we can use B. The center is A. So this is called is an open disk. Sometimes, all right, this is the center, and this is the radius. So there are many ways to describe a neighborhood. Okay, so this neighborhood actually, sometimes people call this an open disk with center A and radius right here. Okay, second geometric object is called the open annulus. Okay, an open annulus actually is Z such that rho 1 less than Z minus A less than rho 2. Okay, where okay. So when rho 2 are positive, and then rho 2 is bigger than rho 1. So it's called the open annulus. Okay. So the one called closed annulus is a subset okay. So sometimes people use A annulus, and the center is A. Okay, rho 1, rho 2. Okay. And this is called A. Far here, or sometimes just far up to over the A to indicate it's closed, to include the boundary. Okay, so and the half planes, right? For example, and the real part of Z is greater than 0, or a set of all complete numbers such that the real part of Z is less than 0, or such imaginary part of Z is greater than 0, or imaginary part of Z is less than 0. Okay, there are a lot of half planes. Okay. First, open state. Okay. Yes. All right. Now for each Z in the set, there exists a neighborhood in set U of Z such that the neighborhood U is contained in S. Okay. So a set is called an open state if that for each point in the set X, we can find a neighborhood of Z. A neighborhood of Z is an open disk like this one. Okay, so we can have that. So if this is A here, then a neighborhood. This is zone. Okay, so this is a neighborhood. Okay, and if A is here, so we have an open annulus is so an annulus is just like a wheel, okay? So no one go to here. The open annulus does not include the boundary, okay? But for cross annulus, that it will include the two boundaries here. Okay. For an open state, okay, this is an open state. So that means that if you, for each Z here, we can find a neighborhood. This neighborhood is contained in the open state. So these are all some geometric objects. And later on, you will see open annulus play an important role in complex analysis. Six, connected set. Yes. Okay? For any 2 points, C1, Z2 in S. Okay? There exists a chain of finitely many line segments. Okay? Showing Z1 and Z2. Okay. So in the complex plane, this is X. Right? So when we say that X is connected, if we find Z1 and Z2, we can find a chain of finitely many line segments to join them. So what is the line segment? Well, we can go here and then go here, and here, and here. Okay, so we have 1, 2, 3, 4, 4 line segments. And we say it's a chain, means that one end is another, the end of another line segment. Okay, so they will become to a pair. Okay. All right, so and we say that a subset is connected. It must have this property. Okay, so we can connect any 2 points by a chain of finitely many line segments. It's very important to have finitely many. All right? Otherwise, it's very the geometry will be very strange. So this is called connected. 7. We talked about connected set before, right? Domain. What is domain? Domain is an open connected set. Alright? So if a set is open here, means that for every point we can find a neighborhood contained in the set. Okay, it's an open set. And also it's connected, means that any point can be connected by a chain of finitely many line segments. Okay, so it's called domain. Okay. What is cross set? Cross set, well, is the complement of an open set in C. Okay? So the complement of an open set is called a cross set. 8, 9. A boundary point. Okay? Z of a set. Okay? Of a subset of the complex plane. Right? So we say boundary point. It means that every neighborhood of Z, okay? Every neighborhood of Z contain, right? Contains both points in X and the points in the complement of X. Okay, so we have that is X. The boundary point here, if you have a neighborhood, you will find that it includes points in X, also in the complement of X. So every neighborhood has this property. Every neighborhood has property. Then we call that point is called a boundary point of X. This is going to be the set of all boundary points of a set. Okay? So if we collect all boundary points together, it will be denoted by these DS operations. 11, a region X, a domain okay, it's a domain union part of the boundary point of the domain. Okay, so we talked about the region before. Okay. So basically, we will study those geometrical objects in the complex plane. Okay, in the complex plane. So before we end the lecture, I would like to put a definition of a complex function. Okay, it's a function. Okay, f from a subset x of c to c. Okay, so f is x to c, and x is the subset of the complex plane. Okay, so it's called complex function. It means that the domain is a subset of the complex plane, and the codomain is just the complex plane itself. Okay, so the independent variable is complex number, and the dependent variable is also a complex number. Okay, so you have to know that. Complex to complex. Okay, complex to complex. So z goes to fz. Right? Complex to complex. And then such kind of function is called a complex function. A complex function. And so an example is that w is fz, and we said it's z squared plus z. Okay. So now we know it's a complex function. All right, defined. So from here we know the domain. The domain is that. So the defined domain is any complex number in the complex plane. So defined on C. So x is equal to the whole C. Okay, x is equal to the whole C. All right. Okay, and another example. Okay, for this one, so this is a complex function defined an open annulus. Actually, is x what is minus the 0, because 0 is undefined. So what is that? This is annulus 0, 0, and then infinity. Okay? The first 0 is the origin, the complex number 0. The second 0 is the real number 0. This is our A, this is our row 1, this is our row 2, okay? Yeah. But this is spatial, okay? This is kind of spatial type. And so the domain is not the whole complex plane here. It is very obvious that z cannot be equal to 0. Okay? So basically the rest of this method we will consider complex functions. Okay, we will consider the differentiation of complex functions and their integrations, and then some of the behavior, right? A lot of some behavior, right? So this is for today. Okay. And well, we have second midterm, right? On Thursday, start at 12:40. Okay, earlier. Yeah, so please come earlier. 12:40. Okay. And we'll cover basically chapter 12. But sometimes, you know, some of the material in chapter 12 depends on material in chapter 11. So I recommend you to bring the textbook and the supplements chapter 11 here. Okay? So someday you will need to refer to that material. Okay, so good luck. Bye.